In this video, we're going to start chapter 3. And chapter 3 is on intermolecular forces, so the connections between particles, and then also on functional groups. And I want to talk about functional groups first. So functional groups. So essentially the deal is there's a lot of different types of organic molecules. So what we do is we group them together into what are called functional groups. And all the molecules within the particular functional group have similar structural and then also physical and chemical properties. You can kind of think of the functional group as being the reactive part of the molecule. So we're grouping them together in like types. That makes any sense. I think once you actually start seeing some of the functional groups, that'll make more sense. So our first one is an alkane. And an alkane is going to just contain carbon and hydrogen. So no oxygen, no nitrogen, only carbon and hydrogen. And then all of the carbons have single bonds between them. So contains carbon-carbon single bonds. So an example, right, that would be an alkane. It only has carbon and hydrogen, and all of those carbons are connected with single bonds. Molecules that just have carbon and hydrogen in them are called hydrocarbons. So an alkane is a type of hydrocarbon. Not hydrogen, hydrocarbon. So there's going to be other types of hydrocarbons, and alkane is just a particular type of hydrocarbon. Again, if it contains only carbon and hydrogen, it's a hydrocarbon. So hydro for hydrogen, carbon for carbon. Our alkanes are going to follow the formula CnH2n plus 2. So if I look at this one I just drew, I have 4 carbons, right? There's one here, one here, one here, and one here, so C4. So N in this case is 4. If I was to take 2 and multiply it by 4, I get 8. Add 2 to it, I end up with 10. So this molecule, this alkane, should have 10 hydrogens on it. And if we go and count, there's, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? None of those carbons have a charge on them, so we know that they have 4 bonds. So you would just count up to 4 to get the rest of those hydrogens. If it follows that formula, it is said to be saturated. So C4H10 would be considered a saturated hydrocarbon, right? It follows that formula and it only has carbon and hydrogen. So we could say that this is a saturated hydrocarbon. We could also say it's an alkane. Alkanes will always be saturated hydrocarbons. Right? If we were to do another example, it also just has carbon and hydrogen in it. All of my carbons have single bonds. And if I go and count the number of carbons, I have 1, 2, 3, 4, 5, 6. And then using our formula for saturation, I would take 6 and multiply by 2, which is 12, and then add 2 to that, I would get 14. And then to just double check that, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 hydrogens on there. So again, this would be considered a saturated hydrocarbon. Again, it's an alkane. That's kind of redundant because alkanes are saturated hydrocarbons, with one exception, and those are cycloalkanes. Cycloalkanes are not a separate functional group. They're under alkanes. So that's why I put a squiggly line instead of a straight line. So functional groups is my main heading. Alkane is one of my functional groups. A cycloalkane is a type of alkane. It's not necessarily a separate group. It still just contains carbon and hydrogen. So it's still a hydrocarbon. But this is actually considered unsaturated. Unsaturated means it's going to have less hydrogen than this formula. So it would have less, if I had 6 carbons, it would have less than 14 hydrogen, and then it would be considered unsaturated. And what these are, it's still carbon-carbon single bonds because it's a type of alkane, but those are in the form of a ring. So carbon-carbon single bonds connected into a cyclic structure. So if I was to take 6 hydrogen and put them in a ring, it's still just carbon and hydrogen, so it's a hydrocarbon, it's an alkane. All my bonds have single bonds, all my carbons have single bonds. But if I was to count the number of hydrogen that I have on here, I just have 2 on each carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C6H12, it's not saturated, right? It is unsaturated. To be saturated, I would have to have 14 hydrogen on there. So an cycloalkane is a type of alkane, but it happens to be unsaturated instead of saturated. My next functional group, maybe I'll number these. These aren't really in any particular order, but we'll just number them so we can keep track of things that are functional groups and things that aren't. So I'm not going to put a number on cycloalkane. It's a type of alkane. And then my second one, an alkene. So we're just changing the A in alkane to an E for alkene. And these are also going to be hydrocarbons. So they contain carbon and hydrogen only. So it is a hydrocarbon. But it has at least one, so it contains at least one, it could be more, carbon-carbon double bond. These guys are always going to be unsaturated. Every time we add a pi bond between 2 carbons, we actually have to remove a hydrogen from each of those carbons. Otherwise, we end up with too many bonds. So, example, if I was to do this one, I have a double bond between my middle 2 carbons, right, that pi bond. I have C4, and then if I was to count my hydrogens on this, I have 1, 2, 3, 4, 5, 6, 7, 8. So H8. So these guys are unsaturated. Right? Again, to be saturated, it has to have 2N plus 2 hydrogen, the number of carbons being N. So at least one carbon-carbon double bond, right? At least one pi bond. Our next one is an alkyne. So this time changing the E to a Y. It's also a hydrocarbon. It's also going to be unsaturated. And what's my trend? Alkanes have all single bonds. Alkenes have at least one double bond. What's this one going to be? If you had to venture a guess. Yeah, good. One triple bond. At least one carbon-carbon triple bond. So it's 2 pi bonds. Be careful. though, to use that as your way to explain it, because if you had an alkene with 2 double bonds, it still has 2 pi bonds. So these are 2 pi bonds between the same 2 atoms. It's easier to just say it has a triple bond. So remember, these guys are linear. So this one has 4 carbons. Sorry, I didn't use blue for my example this time, C4. And then if I was to count the number of hydrogens, the carbons right here that have the triple bond between them do not have any hydrogen on them. They already have 4 bonds, right? The triple bond and then the bond to the end carbon. So 1, 2, 3, 4, 5, 6, C6. So alkenes and alkynes and cycloalkanes will always be unsaturated. So an alkene, unsaturated hydrocarbon, it has at least 1 triple bond. An alkene, an unsaturated hydrocarbon, has at least 1 double bond. A cycloalkane is also unsaturated. It has single bonds, but they're in the form of a ring. And then if they're straight chain form, I have an alkane, which happens to be saturated. Again, to be saturated, it's always going to follow this formula. My next functional group that we're going to do is an alkyl halide. I have heard them called haloalkanes before. I don't really use this word that much, other than right now to tell you that sometimes they're also called that. So if you see haloalkanes, that's an H-A-L. It's an alkyl halide. So this contains a halogen bonded to a carbon. And that carbon that it's bonded to does need to be an sp3 hybridized carbon. So it contains a halogen bonded to an sp3 hybridized carbon. We actually have 2 chapters, chapter 7 and 8, on alkyl halides and reactions that they undergo. So it contains a halogen bonded to an sp3 hybridized carbon. Most organic textbooks are actually set up in terms of functional groups. So we also have a chapter on alkenes and a chapter on alkynes and a chapter on alkanes this semester, and one on alcohols, which will be our next functional group. And then the other functional groups, you'll actually learn about those. You'll learn now what they are, but then you'll talk about their reactions and naming and all that kind of stuff in 236. So an example, we'll just stick a fluorine on here. This would be an alkyl halide. It could have more than 1 fluorine, but it needs to have at least 1 halogen bonded to an sp3 hybridized carbon. So remember our halogens. I'm going to do another example with an X. X can be fluorine, chlorine, bromine, or iodine. So if I draw another example, I could do it in a ring too. It's still going to be considered an alkyl halide because that carbon that halogen is bonded to is sp3 hybridized, right? There is a hydrogen on that carbon. Number 5, alcohols. So alcohol functional groups contain oxygen atoms, and specifically it's going to contain what's called a hydroxyl group, and I'll define this in a minute. So hydroxyl group bonded to a carbon. And then that carbon is generally going to be sp3 hybridized also. So what a hydroxyl group is, and this is not a functional group, it's just kind of like a little structural characteristic. That's kind of a weird way to call it, but a hydroxyl group is an OH group that's covalently bonded to something. So like OH with a negative charge was a hydroxide ion, right? This is a covalent bond. So a hydroxyl group has an OH group with a covalent bond. The way we would often designate something that's a covalent bond is I would just put like a little squiggle through it. And that's just saying that that is bonded to something else. So you don't think it's a charge. We're kind of showing that that group is bonded to something. Because I'm going to make an alcohol, I'm going to bond it to an sp3 hybridized carbon. So that would be an example of an alcohol. You can make them cyclic if you want. You can make them short. You can make them long. You can do all sorts of things with them. But if you have a hydroxyl group bonded to a carbon, it is going to be an alcohol. Do be careful. Make sure that when you're connecting these, you draw the line between the carbon and the oxygen, right? It's not bonded to hydrogen. So like the first one I did, do not do this. And a lot of people do when they're first learning, probably because you're just not realizing that you can't do it. Don't do that. Now I have carbon bonded to hydrogen and hydrogen bonded to oxygen, and I can't do that. So make sure you actually connect them to the atoms that they're connected to. Like you can be a little messy, but if you get too messy that you're actually connecting your atoms incorrectly, I will mark it off. So just be careful. If we look at my little picture here, it's the oxygen that's bonded to the rest of my molecule. My next one is going to be an ether. And an ether is going to contain a carbon-oxygen-carbon bond. So a carbon-oxygen-carbon bond. You could make the signs symmetrical. You could make the two sides unsymmetrical. Make it bigger. We could have a cyclic ether. If I want to put the oxygen in my ring, totally cool. It's still a carbon-oxygen-carbon bond, right? And in the alcohol and this ether, I do have two lone pairs on those oxygens, right? Because I don't have a charge on them. I could protonate them or deprotonate them, and then they would have charges. But oops, that guy, he's wrong anyway. We don't need to fix it. So carbon-oxygen-carbon bond is our ether. Number 7, and that's an amine. And an amine is going to contain a nitrogen bonded to at least one other carbon. And those carbons are generally going to be sp3 hybridized also. So nitrogen bonded to at least one other carbon. So nitrogen will bond it to, let's do something structural, CH3. There is a lone pair on there, so that would be an amine. You could bond that nitrogen to two other carbons. We'll do this one using some skeletal structures. You could bond that nitrogen to 3 other carbons. In any of those cases, I have a nitrogen bonded to at least one carbon. We do differentiate these between primary amines, secondary amines, and tertiary amines. Primary means the nitrogen is bonded to one carbon. Secondary means the nitrogen is bonded to 2 carbons directly, right? This nitrogen, I'm going over in pink, is bonded to this carbon and this carbon. And then tertiary, this nitrogen is bonded to this carbon, and this carbon. So it's bonded to 3 other carbons. There's a few more. This is our first big chunk of memorization. I'm sure you've heard the rumors that there's a lot of memorization in organic. So this one, what should we do next? Let's do an aldehyde. And an aldehyde is going to contain a carbonyl, which I'll define here in a second. Bonded to a hydrogen. So what a carbonyl is, this is kind of like a hydroxyl group. It's not a functional group, but it's like a little structural characteristic. I wish I had a better way to call it. So carbonyl. A carbonyl is going to be a carbon with a double bond to an oxygen. So that's a carbonyl. If you see that. So when I say a carbonyl bonded to a hydrogen, I have a carbon that has a double bond to an oxygen, and then that carbon is bonded to a hydrogen. So that is my carbonyl. So an example. We'll do this one upside down. And then there's a hydrogen there. Remember that hydrogens that are bonded to carbons, you don't have to show. This technically isn't a carbon. I mean, it is, but it's a carbonyl, so I'm going to show it. I know that makes no sense, but I am going to show it when they're bonded to carbonyls. You could say that, no, that wouldn't work. I was just going to say bonded to sp3, but if you were to do an alkene or an alkyne, you don't have to show the hydrogen. So I guess it is standard if you have a carbonyl. Just think of it as not a carbon and a hydrogen. Think of it as a thing. Just like polyatomic ions, right? I don't think of hydroxide as oxygen and hydrogen. I think of it as hydroxide, right? A hydroxyl group we're going to do the same thing with. A carbonyl we're going to do the same thing with. So I have a hydrogen bonded to a carbonyl. They always have to be on the end. If I was to put the carbonyl in the middle, I'm not going to have a hydrogen bonded to it, right? That carbon can only be bonded to one other thing on each side. So if it was bonded to a carbon on each side, it can't be bonded to a hydrogen. We are going to have 3 others. Is that right? Sorry, I'm talking to myself. Yeah, 4 others that have aldehyde, that have carbonyls in them. Of all the ones that I have, this is the only one that has an H in the name, and that's how I remember this one. I don't have a lot of tricks. I only have 2 tricks, and this is one of them. But of all of the carbonyl containing compounds, the only one that has an H in the name and the only one that's bonded to a hydrogen is aldehyde. So hopefully that will help a little bit. Number 9, a ketone. A ketone is going to be the one with the carbonyl in the middle. So this is going to have a carbon, a carbonyl, and then a carbon bond. So it contains a carbonyl bonded between 2 carbons. So a carbon, carbonyl, carbon bond. An example. So I have a carbon here, I have my carbonyl in the middle, and then I have another carbon. So this would be considered a ketone. Number 10, carboxylic acid. And a carboxylic acid is going to contain a carbonyl bonded to a hydroxyl group. So a carbonyl bonded to a hydroxyl group. And carboxylic acids actually are acidic. I'm just redrawing that so it's neater. Acetic acid is a carboxylic acid. So this is acetic acid. So it has a carbonyl bonded to that hydroxyl group. Two more that we're going to cover. There are other functional groups, but these are the ones that I want you to know for now. We are going to add a couple more, however, as the semester goes on. This one's an ester. Be careful not to get ester and ether confused. They look kind of like each other, like the name, they both start with an E, but they're different. So this one is going to contain a carbon bonded to a carbonyl, bonded to an oxygen, bonded to another carbon. And honestly, this could be a hydrogen instead. So you can just think this part if you want. Carbonyl, oxygen, carbon bond. And of course, we can read right to left or left to right. So it could be a carbon, oxygen, carbonyl bond. So it contains a carbonyl, oxygen, I'm just going to write it out, carbon. And then one more, and that's an amide. Actually, depending on who you have for lab, they might call it what do they call it? Amide, I think. I learned it as amide. If you're from the Midwest, that's how you learned it. Amide is how I've heard other people call it. I like amide because it goes with amines and amides. And that's how I learned it. But this one is going to contain a carbonyl bonded to a nitrogen. And then that nitrogen can be bonded to 2 hydrogen, 2 carbon, or 1 carbon and a hydrogen. Remember, nitrogen to be uncharged, right, to be neutral, is going to have 3 bonds. One of those bonds, however, has to be to a carbonyl. So it's going to have a carbonyl bonded to a nitrogen. And we can classify these as primary, secondary, and tertiary also. So if I was to do this one and then just put 2 hydrogens on it. They don't always have to be upside down, but I find that if I always draw them this way when I'm explaining it and then never give folks an example of one that's upside down, then it's easy to not recognize them when they're upside down. So this would be a primary amide or amide, depending on who you're talking to, secondary, and then tertiary. But in all of them, I have a carbonyl bonded to a nitrogen. I don't think I gave you an example. Yeah, an ester. So this one, carbonyl, and then oxygen, and then carbon. So that makes that an ester. So the other trick I have, it's not much of a trick. So besides the hydrogen and the H and aldehyde, is amine and amide. So the word amine and then the word amide, they only differ by 1 letter. So it's really easy to get those 2 mixed up. And the amide is the one that has the carbonyl in it. So if I look at it, if I look at this word, the D is like sticking up outside of that yellow highlighter, right? It sticks up. And then if I go up here and look at this, my carbonyl, right? That sticks up. So that reminds me of the D. If I look at this, there's nothing sticking up. So we'll do a couple examples where I draw some big organic molecules because we can have more than 1 functional group per molecule. So I'm just going to draw some big obnoxious things, and then I'm going to ask you to hit pause, circle and identify the functional groups that you see, and then hit play again to check your work. And I get that you're going to have to look at your notes right now because you haven't memorized these. Eventually, the goal, though, is to be able to look at a functional group without looking at your notes and be able to recognize them. And again, like I said, there are other functional groups, and we will be adding some throughout the semester, but these are the ones that I'm going to stick to for now, the ones that I'm going to ask you to know. So I'm going to draw some big messy things here. Sorry, that's supposed to be a double carbonyl. Okay, so I'll do the first one just so you can kind of see what I'm looking for. So I have right here a carbon bonded to a hydroxyl group. So this is an alcohol. So please hit pause, go through and identify the functional groups that you see, and then when you're ready, come and check your work. Okay, hopefully you guys did that. So this one is an alkene. I have a carbon-carbon double bond. This one is an ester. Guess I probably should include that carbon in my circle. So ester, I have a carbonyl bonded to an oxygen bonded to another carbon. This is an amine. Specifically, it's a secondary amine. If you didn't get secondary, that's okay. And then I have a carbon bonded to a bromine, so this would be an alkyl halide. I'm just gonna stick that bromine on there a little better. It's kind of messy. Let's do some more. Okay. So same idea. Please try these on your own, and then when you're ready to check your work, come back. Okay, so I have another alkene, right? Carbon-carbon double bond. This one might have been a little tricky because I put it into a ring, but it is an amide, right? It has this carbonyl here bonded to the nitrogen. So an amide or amide. Carbon-carbon triple bond is an alkyne. And then this last one is a carboxylic acid. So I have a carbonyl bonded to that hydroxyl group. Let's do another. Sometimes it just doesn't select good. Okay, so same idea, please try it on your own. Okay, so carbon bonded to a hydroxyl group is an alcohol. Here I have a carbon, oxygen, carbon, so that's an ether. Be careful not to get it mixed up with ester. Another alkyl halide. So a carbon bonded to that halogen. This one is an aldehyde, carbonyl bonded to that hydrogen, and then a ketone, which is incidentally the most misspelled of all the functional groups. It's not, not K-E-Y-T-O-N. It's not ketone. I mean, it's ketone, but not spelled like a key. Not that. So ketone. So please practice these. It is kind of a big chunk of memorization. So my advice for memorizing, and at least this is what works for me, like if I just sit here and stare at my notes, I'm not going to learn it. Like my brain is just going to be off thinking about something else, even though I'm staring at it. I actually always have to engage with something to do well. So I would just get out some scrap paper and start writing them down. Like just make like practice lists. I would just have in this class tons of scrap paper just everywhere with just notes by writing stuff over and over again. So we could just do alkane, and you could just give yourself like a little example for these ones. Alkene, at least a double bond. I mean, you could write out more words than that if you wanted, but just for practice, this guy's got to be linear, right? An alcohol, carbon bonded to a hydroxyl group. Oop, we forgot alkyl halide. Carbon bonded to a halogen. I think you guys get the idea. Carbon, oxygen, carbon. So just make yourself lists. If you do this enough times, like, you're gonna learn them. It's like back if you had spelling words and you got them wrong and you would have to write them down 10 times each. It's that sort of concept. So I would, do the homework problems, the practice problems from the book where you're identifying functional groups. But then also I would just, repetition, I think, is the key when it comes to memorizing.